Good morning, everyone. Are there any questions before we get started? No? All right, today we're going to talk about conditional probability. But before we do that, we covered a lot of different techniques for solving probability problems on Friday. And so I thought I would start by giving a quick review and then giving you 3 warm-up problems. In fact, you've already been working with conditional probability using the probability trees, so it's a very sort of natural thing to think about. But when we introduce the notation, sometimes it can be a little confusing. So I thought we'd start by revisiting some problems that use probability trees and other techniques, and then from there move into conditional probability. So just to review, what different ways we have seen so far to compute probabilities. At the top is the counting way. This is really very useful if you don't have a lot of things to count, and if all of the possible outcomes are equally likely. You can go wrong if the things are not equally likely and you use this counting argument. The next way is complements. So to figure out the chance of something happening, you figure out the chance it doesn't happen, and then use the rule 1 minus that chance would be the chance that it happens. Then we have our trees, and with the trees, trees are very useful if we are thinking about computing probabilities from the point of view of walking through steps that happen in time. First this happened, and I know the chance that that happens, and then given that I know that, here's what happens in the second step. You sort of build up these probability trees, and then there's some very simple rules for computing probabilities from them. We'll do an example this morning. Symmetry says, oh, I know that should be the same as this other thing, and I know its probability, therefore I can figure out the probability. Equivalent problems are often sort of reducing the complexities. For example, with the cards, when we asked what's the chance you draw a heart, rather than using the counting rules of, well, how many hearts are, there's 13 of them out of the 52, we could say there are 4 suits, and they're all should be equally likely, so it's 1 in 4. And the last one, which was not there on Friday, is Venn diagrams. And I also lump in with Venn diagrams tables, sort of making tables of all the possible different outcomes and then computing probabilities based on that. And we'll give an example of Venn diagrams today. All right, so I'm going to give you 3 problems. And I'd like you to, for each of them, take a minute or so to try and solve them. And then we'll go over solutions. And I picked these 3 because each of them sort of naturally you would use one of these methods, and I think all 3 of the methods would be represented in the solutions. All right, so the first one's a very slow warm-up. There are raffle tickets that are numbered 1, 2, 3, 4, all the way up to 500. So there are 500 raffle tickets for a prize. You put them all in a hat or a box or whatever, and you mix them up really well. And one number is drawn out, and whoever's holding that ticket that corresponds to that number wins the prize. So I'm holding 3 tickets, numbered 17, 93, and 202. My friend is holding 4 tickets, numbers 21, 101, 102, and 398. So I have 3 problems here. What's the chance I win? What's the chance my friend and I both lose? Neither my friend nor I win. And what's the chance that the winning number is 1 away from one of my friend's numbers? All right, so why don't you just take a minute to scratch out what you think the solutions are. And when you're doing that, think about what of the, I'm going to quick back up here. Think about these different ways: counting, complements, trees, symmetry, equivalent problems, and Venn diagrams. And which of these do you want to use? Do you want to see these, or do you want to see the problem? Problem. Okay. There's the problem. you ready? Let's take a look. I am going to move over to the document camera so that we can solve it together. Can somebody tell me how they would address the first part of the problem? What's the chance that I win? Oops, do you see it there? Yes. For some reason, I don't. Oh, there we go. What's the chance that I win? Yeah?
I just use the counting method, and since you have 3 tickets and each one's equally likely to win, I just counted it up and said it was 3 out of 500.
That sounds like a good approach, is to use the counting method. This is a very simple problem where every ticket is equally likely, so it makes sense that we would want to use the counting method. I am holding 3 tickets, so the chance that I win would be 3 out of 500. Now, what's the chance that, question in the back?
You count your friends' tickets as you already know what they are, so if you have 496.
I do know my friends' tickets, but still there are 500 tickets in the entire bucket, right? And so the chance that I win is a chance that one of my tickets gets picked out. Good question. Good to ask questions. How about, yes? Can you do 1 out of 500, then 1 out of 499? There's only one ticket that's being chosen, and then that ticket has to match mine. And so there are 3 ways that could happen. So we want to think about it as like, how many ways could the ticket that comes out of the box match mine? There are 3 ways that it could match mine. It could be a 17, a 93, or a 202. And there are 500 possible ways that a ticket could be drawn. So it's only one draw. If you're used to the sort of mutually exclusive rule, I could win if number 17 is drawn, or number 93 is drawn, or number 202 is drawn. So we could use that way of solving it. Maybe that's easier for you to see. I could say, well, that's the probability that 17 is drawn. Maybe this is easier for you to see. Or 93 is drawn. Or 202 is drawn. So those are the 3 possible things that could happen. They are mutually exclusive in the sense that you can't draw both of them. The 2 things can't happen at the same time. So I could then add up these individual probabilities. 17 is drawn, plus the probability 93 is drawn, plus the probability 202 is drawn. So the chance 17 is drawn, well, there's only one 17 in that bucket. They're all equally likely, so it's 1 in 500. Same with 93. Same with 202. And so that's another way to solve the problem. And maybe that makes it clearer to you why it's not the way you said it. Yes?
There's going to be 2 drawings with the probability change with probability less than 1%.
Yes, the probability would definitely change. Because when you make 2 drawings, you don't put the ticket back in. And so we'd have to say, well, that's the chance that one of my tickets appears, at least one of my tickets appears on one of those 2 draws. Right. How about the next part of this question, which is, what's the chance both my friend and I lose? How would you solve that one? Yeah? Use the complement rule? Right, so use the complement rule plus what we already figured out how to solve the problem. So we already figured out to solve the problem in terms of what's the chance that I would win. We can now say, what's the chance that I win or my friend wins? And we know that since together we have 7 tickets, the chance that my friend or I win is 7 in 500. So we would use the complement rule here. To say the chance that my friend or I win should be 7 out of 500 because together we have 7 tickets. And so the complement of that is 1 minus 7 over 500. That's the chance that neither my friend nor I win. And that's 493 over 500. Any questions about that one? No? Now the last question of here said, okay, what's the chance that the ticket drawn is 1 away from my friends? You were going to say? Is it 10 out of 500? How'd you get that?
Wait, was the question 1 away from the friends tickets? Is it including the ones that are actually?
Very good. I left it ambiguous. And that only because it's just to make the point of you should be really clear as to, was it 1 away from my friends and he didn't win? Or 1 away from my friends and he could have won? Why is this even an issue? He had 2 tickets with numbers that were right next to each other, 101, 102, and therefore 101 would mean he'd won and it was 1 away from him. Right. So let's answer it as he might have won, he might not have won, just it's 1 away. And therefore, and then we'll answer it the other way. So it could be what? We could list them all. Let me get another piece of paper. We could list them all, and there would be 20, 22, 100, 102, 101, 103, 397, and 399. And so it's 2, 4, 6, 8, right? So I don't know how you got 10. How'd you get 10? Did I do?
I was counting the numbers themselves also.
So I didn't even answer your question. Okay, so that's 8 out of 500. If we go the other way and say, what if he just missed by 1? So this gets to the point of you need to be really clear on what the question is. So what's the chance that he just misses winning by 1, meaning 1 number away from one of his tickets? What are now the tickets that could be drawn so that he just misses by 1? He goes, I just missed by 1. We all do that, right? Yes? Sure.
We're doing 1 away from the friends numbers, and why are we including 1 if those are
Well, that's because it's not answering the bottom question. 101 technically is 1 away from 102, which is one of his tickets.
But it's not 1 away from his numbers. As in, like, maybe just different interpretation.
What?
Interpreted as, like, 1 away from winning.
Yeah, that's the second question. And therefore, you're right on. And therefore, we would not include 101 and 102 because he would be winning. That's right. So to answer the question this way, that he's just 1 away from winning, means we wouldn't include those 2. That's your point, right? Yeah. Okay, and so therefore, to be 1 away from winning, it's, in fact, 6 out of 500. So that question was not well worded, and so it led us to different possible solutions. Okay, I want to go back to the next question. 2 dice are rolled. What's the chance the same number is rolled? At least one of the numbers is 6. The maximum number is either a 6, a 5, or a 1 once you get this. So I'll tell you what I find is useful when I solve this problem is to distinguish between the 2 dice. It doesn't say that in the problem, but I find it easier to solve the problem. I think of one as colored red and the other is colored blue. And I roll those 2 dice. And so I can kind of keep track of the 2 dice that way. So why don't you take a minute to try and solve this problem? Shall we start? Yeah? Some of you are ready? 30 seconds? Okay. Yes, question? So when you roll the two dice, one could be a 1 and the other could be a 6. The maximum of those two numbers is 6. When you roll it again, one could be a 4 and the other's a 5, so the maximum is 5. So that question, the last one, is saying, of the two numbers, what's the biggest one? So what's the chance that the biggest of the two numbers showing is a 6? All right, let's take a look. So somebody tell me how you solved the problem, or at least started solving. Maybe you didn't finish, maybe you didn't get all three, but what did you do to try and solve the problem? Yeah?
For the first one, I got 1 out of 6.
Uh-huh. How'd you get that?
Because I assume, well, I assume like the first die is rolled, and some number could come up, any number really, so it could be a 3, and then the next number has to match it, so there's a 1 out of 6, no matter what the number is, chance that that number will be matched.
That's a really nice way to think about it. So what you did was you said, they have to match. So I've got my red and my blue die. I'm going to throw my red die. Whatever number appears there, whether it's 1 through 6, now I know that the next one has to match it. And so the chance it's going to match it is going to be 1 out of 6. That's good. So you said we want to look at the probability that the blue die matches the red one, whatever number that might be, and that should be 1 out of 6. How about the next one? The chance that at least one of the two dice lands 6. Did anybody get this? You? No? Yes?
The chance is 1/3. The chance that the first one will be 6 is 1 out of 6. The chance that the second one will be 6 is 1 out of 6. You have a possibility. Only one possibility.
You're really close. So you said the chance that the red die lands 6 would be 1 out of 6. That's right. The chance the blue die lands 6 is 1 out of 6. That's right. Are those two things mutually exclusive? Could they happen at the same time? Yes. And so we've double counted one possible event, and that is the chance that they both land 6. And so it is 1/6 plus 1/6, but then you have to subtract off something. You've double counted the chance that they both land 6, so you subtract off 1 in 36, and then you get it. And yeah, so the way I would solve this is by drawing a picture. And this is where either Venn diagrams come in or tables. I really like to use the table idea. So I'm going to draw a table. That's 1, 2, 3, 4, 5, 6. This is my red die. And then my blue die is across the top. 1, 2, 3, 4, 5, 6. That's my blue one. And this little table is all the possible outcomes. So I'll ask you, how many possible outcomes are there? I heard it, I think. 36. Right, each one of those cells in this table corresponds to an outcome. This one here corresponds to the red die landing 1 and the blue die landing 1. Which cells correspond to at least 1 6 is rolled? I see you. What are you saying? The bottom line and the right side. So in this table, if the red die lands 6, then at least one of them's landed 6. There it is. There are 6 ways for that to happen, obviously, and so it's 1 in 6. Now, on the other hand, the blue die could also land 6, and I would have at least 1 6. And so those are all the possibilities. How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. If we count across the row and up the column, or down the column and across the row, either way, we see that there are 11 possibilities. And so it is 11 out of 36. So let's go back to the way that you were solving the problem. You could say, well, that could be the red lands 6 or the blue lands 6. And I'm asking, what's the probability that that happens? And there's a little or here. So that's the probability that the red lands 6 plus the probability the blue lands 6, which is where you're headed. But I have counted now this chance twice. And so I need to subtract off the probability that the red lands 6 and the blue lands 6. And if I do that math, I get a 6th plus a 6th minus a 36th, which is 11 over 36. So there are always many different ways to solve a problem. Though the first one with the chart is sort of like a Venn diagram approach. We're actually looking at all the different possible outcomes. The next one is using the mutually exclusive rule that says if you're looking for the chance that something happens or something else, it's always the probability this A happens plus the probability B happens minus any possibility of the two happening together. Yes? Yes? So, okay, so good question. Let's revisit the first question using this diagram. And so I want to shade it in slightly differently. It says, hey, what's the chance that they both come up with the same number? So that's an entirely different question. I'll see if I can, I'll use a different color marker, but I'm not sure it'll look different. So you tell me where on this chart of 36 little cells are I see you already are telling me where are they all, the possible roles have the same number? And you're going to tell me.
We start from the upper left corner.
Mm-hmm.
Diagonally down.
So I'll put in little circles like this. 3 and a 3, 4 and a 4, 5 and a 5, 6 and a 6. Those are all the possibilities of them landing the same way. And there are 6 of them out of 36. So that's a different way of solving the first problem. Okay? That's a little bit more straightforward than the other way. The other way is a bit slicker. It sort of says, hey, it doesn't matter what the red die shows, the other one just has to match it. Last question is, what's the chance the maximum is 6? Yes? 11 over 36. So yes, it's exact same as this middle question, right? So that starts to get you thinking about how to answer each one of those. What about the maximum being 5? 9 over 36? And how did you get that? The same process with the 6s. So you come over here, for the maximum to be 5, you have to have the red being a 5 and the blue a 1 and the red 5 and the blue a 2, red 5, blue a 3, etc. They could both be 5, or the blue could be a 5 and the red has to be less than it. And so yes, you get a similar slice of this thing, and it's 9 out of 36. So this one is 9 out of 36. And the chance the maximum is 1 would be they'd both have to be 1. That's that dot there, and that is just 1 in 36. Okay, good. Any questions? Yes?
This question doesn't specify, and I guess it's true, but like it would be different if you said that the max of the 6 and they both have to equal, right?
Yeah, that would only be 1 in 36.
Yeah.
That's right. Yes. All right, let's go back to
Can we do that middle one by complement?
which one? The middle one.
At least one that's
Oh, thank you. Yes, there are many ways to do these. Can we do the middle one by the complement rule? At least 1 is a 6. What's the complement of that? They're not, both of them are not 6, so they're both 5 or less. The chance of that happens is 5, yes? 5 over, yes.
And then 5 times 5 over 1 minus 5 times 5.
They're, right, you're filling in the inner circle. It's 25 possibilities over 36. Yes, very good. Thank you, Mike. All right, next question. Pick a word at random from the following sentence. How, now, brown cow. What's the chance the word has 3 letters? That's the first question. The second says, okay, given the word you've chosen, pick a letter at random from the chosen word. What's the chance the letter is a vowel? Yes, question?
Does it have at least 3 letters or exactly?
Exactly 3 letters. What's the chance the word you draw has exactly 3 letters? Another question? No? Yes?
For B, we're only looking at one word if you want us to go through each word.
Well, in a way, you kind of have to go through each word. So it's whichever one you chose in the first one, which you don't know which one you've chosen. What's the chance you get a vowel? So you sort of have to figure it out for all of them and then combine the results. Are you guys ready? Shall we hear a solution? How about the first one? What's the chance that the word has 3 letters? 3 out of 4, because each of the words are equally likely to be chosen. There are 4 words in the sentence. How, now, brown cow. And 3 of them have 3 letters. How, now, and cow. Getting the next one's a little harder. Has anybody gotten the second part? Yes?
I think so.
You think so?
What I did was, I did 3 over 4, which is the probability of getting with 3
Uh-huh.
letters. I multiplied that by the probability of putting the vowel out of that, which was 1 out of 3.
Okay.
And I added the probability of choosing one with not,
The brown,
yeah, brown.
right.
And multiplied that by the probability of choosing a vowel, which is 1 out of 5.
That's right. Did anybody else do it that way? Yeah, a few of you. So, did anyone use a tree? Did anybody think about using a tree? This is sort of a natural problem to use a tree with because there's a time sequence here. So we can think about first drawing a word. So there's a complex tree or a simple tree. I could draw a tree where I have each branch coming from the tree is a different word. So this would be how, now, brown, and cow. And then the next step is to choose a letter from that word. And so out of each one of these, I could have HOW or NOW or BROWN or COW. So that's listing all the possible outcomes. Now I have to put probabilities on my branches, and the chance that I pick each of those words is equally likely, and there are 4 of them, so it's 1/4, 1/4, 1/4, 1/4. Once I pick a word, to then pick a letter from the word, each thing's equally likely, and so each letter's equally likely, and so for a 3-letter word, it's 1/3, 1/3, 1/3, 1/3, 1/3, 1/3. Brown is 5 letters, so they're each 1/5. And cow is 3 letters, so they're each 1/3. And the question says, what's the chance I draw a vowel? So I could look over here. I could multiply down and see this is a 12th, and for this O, it's a 12th. And for this O, it's a 20th. And for this O, it's a 12th. And so the chance I draw an O is a 12th plus a 12th plus a 20th plus a 12th. Now, is that equivalent to what you did? It is. It's a little more complicated, but it's equivalent. Questions about that? I have a question for you. How do I make a much simpler tree? Yes?
Like, I guess you just have 2 branches from the top because 3 of the words have 3 letters. So you just multiply.
Not only do they have 3 letters, what else is special about them? They only have 1 vowel. So if you know in the end, the only thing you really care about is getting that vowel, how, now, and cow are all sort of equivalent to each other. So this is this notion of simplifying the problem into an equivalent one. How, now, and cow are all equivalent if all we're caring about is did I get a vowel in the end? And the other simplification is what? In the second stage, what would you do? Did I get a vowel or not? So rather than keeping track of I got an H or a W or whatever, and so we could simplify this with a slightly different tree. And essentially, so this is the notion of using equivalence. I could just say, did I get one of the 3-letter words, or did I get brown? That's the choice of picking the 3-letter words. This is getting closer to the solution that was suggested. That's a 3/4 versus a 1/4 probability. And then you just care about did I get a vowel or not. And so coming off of here, I would say, did I get an O or not? Did I get an O or not? The chance I get an O from my 3-letter word is 1 in 3. The chance I didn't get an O is 2/3. Then coming out of brown, the chance I get an O is 1 out of 5. And the chance I did not is 4 out of 5. So now here's where I get a vowel, and here's where I get a vowel. I pick a 3-letter word, and then I get the O. That has a chance 3/4 times 1/3. And over here, if I pick brown and then the O, that has a chance 1/4 times 1/5. And so together, adding across the bottom, I get 1/4 plus 1/20, which is 3/10. 3/4? Did I screw that up? Whoops. I'm right, I think. Okay. Okay, so let's talk about conditional probability here. We are using conditional probability in this tree. So what's going on is that these probabilities down here on this branch is conditional on knowing that you've picked the 3-letter word. So this probability 1/3 of getting an O is given I know I got a 3-letter word, what's the chance I got a vowel? And that's 1/3. Over here, given I know I picked the word brown, what's the chance I got a vowel? And that's 1/5. And then together, this multiplies to say, okay, what's the chance I pick a 3-letter word and I pick the O. So I could say, what's the chance that I have a 3-letter word and you pick the vowel? And so I'm saying that I could write that is, well, that's just the chance that you pick the 3-letter word times the chance you pick a vowel given the information that you picked the 3-letter word. Okay? So that's what I'm doing when I'm multiplying down the tree. And I know that the chance I pick a 3-letter word is 3/4, and given that I picked a 3-letter word, the chance I pick an O is 1/3. And so that's how I get the 3/4 times 1/3, which is 1/4. All right, so now I'm going to put this up as more formal notation. So is everybody clear on it? All right, so we're going to switch back and look at the formal notation. So essentially, if you look at the middle of the screen here, it says we write the probability of A given B, that line, the straight up and down line, is to be read given. So the probability of A given B is saying, knowing that B has happened, what's the chance that A could happen? An example from last Friday is the chance the second card is red, given the first card is red. Says, okay, I know I was drawing without replacement. There are 51 cards left in the deck, and I know 1 red is missing because it was drawn from the first time, and that would be 25/51. So another, if we just sort of think about what I was doing on the tree. So I think I want to start with this bottom one. What's the probability that A and B happen? When we think about the tree, going down the tree, well, that could be the probability that A happens. And then given that A happens, what's the probability that B happens? So it's a product of A happening, and then given that, what's the chance of B happening? So here's another way to think about it, is when you rearrange and you get the definition of the probability of A given B, says, well, that's the chance that A and B both happen, but it's renormalized by the chance B's happened, because you know you're within the restricted set of B happening. So if you think about it, the probability of B given B would then be 1. You know B's happened. You're asked what's the chance B's happened. That's 1. So that sort of makes sense from that renormalization. You want to renormalize because you know you're within the set of, within the event that B has happened. And so when you say, what's the probability that A happens given B? That means both A and B have to happen, and that's relative to B having happened. Given the time, I'm going to skip over Polly's urn. And, well, I want to do one problem that's not here. And then I want to make sure we have time to, all right, so take a coin out of your pocket. So I'm going to go back to the, take a penny, whatever. We're going to divide you up by random. And I want you to flip your coin 2 times and keep track of it. Write down in sequence whether you got a head, then a tail, then a tail, then a head, head. Okay, so flip your coin. Does anybody need a coin? Everybody, you need a coin? I think I got some pennies here.
I know, right?
Yes, you need a coin?
Thanks.
You need a coin?
Is extra credit due today?
Yes. Anybody else? Oh, hang on. Here you go.
Thank you.
Here you go. And share one from your neighbor if I'm running out of pennies. Anybody else? You get a dime, you get a nickel. Oops, I'm sorry. All right, so flip it 2 times. Do a nice flip. As long as it rotates several times and you catch it midair and then turn it over. Oh, I'm getting them back. Thank you. Anybody else need one? Oh, no, you're not done. There's more to it. Okay, write down what you got. Keep track of what you got. So I'm dividing the class up into two kinds of people. Have you all flipped your coin? Written it down? If you got a head followed by a head, you're a liar. Yeah, I'm sorry. It's nothing. That's why it's all at random. If you got a head followed by a head, you're a liar. Anybody else always tells the truth. Ready? Okay. So, here we go. Roughly 1/4 of you guys are liars. All right? Because those are head, head. All right, now I'm going to want you to flip the coin again, but you have to pay attention now depending on whether you're a liar or you always tell the truth. So you're going to take a lie detector test, and the liars get caught. 3/4, where am I? The liars are going to get caught with probability 7 or 8. So I want you to flip the coin 3 times now. If it lands head, 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 you don't get caught. All right? So don't flip it yet because I don't want to know who's a liar, who's not. All right? So the liars are going to flip, and if it's head, 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 you get away with it lying. Now, those of you guys who are telling the truth, the lie detector test usually passes you, but it sometimes screws up. And so if you get a head, 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 you fail the test. Okay? So now flip the coin 3 times in a row. If you get a head, 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 and you're a truth teller, you've just failed the test. If you get a head, 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 and you're a liar, you've managed to squeak through and pass the lie detector test. Have you all flipped? Now we're going to put you on the spotlight. Everyone who failed the test, please stand. If you failed the test, stand. Yeah, we're outing you. If you failed the test, stand. That's it? Okay, come on. If you failed, stand. All right. So look, how many people do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9. These people all failed the lie detector test. Do you think that they're all liars? Do you think most of them are liars? Stay up, stay up. All right. If you actually told the truth, sit down. All right, so 4 people. How many people? 3 people just sat down. So 3 out of the, okay, now you can all sit down. So the rest of you guys are liars, right? So we had 8 people fail the test in our class. 8 failed, but only 5 were actual liars. That's a confusing question. So shall we redo it? So we revisit it? You stood up and you weren't supposed to have?
No, I stood up, but I sat down because I thought that by telling the truth, I actually lied.
Okay. Gotcha. Were you a liar?
Yes.
Oh, yes. So you shouldn't have sat down. So did some people not sit? I didn't. There's 7 liars. Is that true? Like, how many of you actually failed the lie detector test and were called liars? Just raise your hands. You don't have to stand up. 1, 2, 3, 4. Somebody in the back, no? You were standing up, right? 5, 6, 7, 8. Right, I got you. All right, so there are 8 of you who, now I'm confused. There are 8 of you who failed the test, and I believe 7 of you were actually liars. Does that sound about right? You were not a liar? And were you a liar? You were a liar. And everybody else was a liar. So in fact, by chance, we didn't get very many actual truth tellers who failed the test. So 7 were liars? All right. So I could ask you the question, what's the chance someone's a liar given they failed the test? So the test is really quite good at picking people or failing liars, but it also makes mistakes sometimes. We got a little unlucky here in that most of the people who failed were liars. Typically, it should be a slightly larger proportion. All right, so how do I figure this out? Yes?
You're saying, but then when you look at the probability techniques, somehow said that 7/8 of the time that the liars are caught.
Yes.
Not 1/8 of the time, and then comparing that to the data that we have, couldn't that be consistent with the numbers that you provided to us?
Oh, really good question. We need to answer, we need to sort of figure out, it's a slightly different question. So it's a slightly different statement. What does it mean that a liar is caught with probability 7/8? That says the probability you fail a test, given you're a liar, is 7/8. That's not the same as the probability you're a liar, given you failed the test. Okay? And that's a common misconception that people often have, is that they swap the order of those two things. The lie detector test is accurate for 7/8 of the time with liars. It's not the same thing as saying, therefore, 7/8 of the people who fail the tests are liars. How would I answer this question? The easiest way is to use a tree, but it's also this notion of conditional probabilities. So just let's see how much time we have, and I know you guys, I left you with a problem for the weekend, and we haven't gotten a chance to get to it. So let's see if I can really quickly do this. We have the liars, and we have the truth tellers. And then you either fail the test or you pass the test. You fail the test for the truth tellers or you pass the test. The liars, they're only 1/4 of our population. 3/4 are truth tellers. They're going to fail the test 7/8 of the time and pass it 1/8 of the time. The truth tellers are going to fail 1/8 of the time and pass 7/8 of the time. And so here's where we have somebody failing the test. And that's 1/4 times 7/8 plus 3/4 times 1/8. And that's the chance someone fails a test. And it's mixed of liars who are failing a lot of the time and truth tellers who are failing occasionally. And so the chance that you fail the test, that you're a liar given you fail the test, or maybe more interesting is, what's the chance you're a truth teller given you failed the test? So the probability that you tell the truth given you fail the test, so people always say that, right? The test is wrong. I'm really telling the truth, is then 3/4 times 1/8 divided by 1/4 times 7/8 plus 3/4 times 1/8. So it's the probability of the truth and you fail divided by the probability you fail. And that is 3/10. So it should have been roughly 30%, and because we've got small numbers here, roughly 30% of the people who failed were actually telling the truth. That's what we'd expect. We had 8 of you who failed. We'd expect 2 of you to have actually been telling the truth. Only 1 of you was telling the truth. All right? I will let you go. I promise, we will get to Pascal and Fermat's solution. And those of you who have the extra credit assignment, please bring it up.